So we're completing 11.4 notes on page 178. We will come back to 11.3 where we will pick up the two basic types of calculus problems, finding the slope of the tangent line and finding the area under a curve. So let's start with example 1. We're going to finish up limits with finding limits that go to infinity. So the limit as x approaches negative infinity. So as x is moving out here to the left forever, where is this graph approaching? Well, you remember that rational functions have horizontal asymptotes. So if I know the horizontal asymptote, I will also know the limit because that is where this graph is approaching, is the horizontal asymptote. So you might want to stop the video and write these down in your notes. The horizontal asymptotes, there were 3 types. There was same co, which means the degree in the top is the same as the degree in the bottom. And the horizontal asymptote is y equals the leading coefficient over the leading coefficient. There is bottom heavy, and that horizontal asymptote is always y equals 0. And then there's top heavy, which is where we got slant asymptotes, but there were no horizontal asymptotes. So if I were to graph x plus 1 over 2x, it looks like this. You could graph it on your calculator, on Desmos, even graph it by hand, just set up a table. And you can see as x is going to negative infinity, the limit is going to be 1/2. And this is a same co-problem, so x to the first is the degree on the top and the bottom. So the coefficients are 1 over 2. And you can see this looks like it's approaching f of x is 1/2 as x is going to negative infinity. The limit as x approaches positive infinity, that's going to be way out here on the right side of the graph. And you can see that this value again is approaching the horizontal asymptote, which is also 1/2. Limits at infinity of rational functions. So this says the limit as x approaches infinity of 1 over x raised to any power is going to always be 0. Let me give you an example of that. So if we had the limit as x approaches infinity of the function 1 over x. So that's just your basic reciprocal function. That function, remember, looks like this, where you have 2 branches, and we have horizontal asymptote at y equals 0 because it's bottom heavy. And so as I move to infinity out here, the limit is equal to 0. Now, if I did the limit as x approaches negative infinity, out here, this is also moving towards the horizontal asymptote of 0. Looking at example 2, find the limit as x approaches infinity. So we will be looking at out here, what is f of x approaching? And it looks like it's approaching 4 just by looking at the graph. So if you wanted to use the horizontal asymptote, you would need to combine this into one fraction. So to do that, you would have the limit as x approaches infinity. And then if you have 4 over 1 subtract 3 over x squared, the common denominator is x squared. So you'll multiply the top and bottom of that by x squared. That's going to give us the limit as x approaches infinity. We're going to the right of the function 4x squared subtract 3 all over x squared. You can see that this is same co. They have the same degree. And so we would be looking at the leading coefficient, which is 4 over 1. And so the limit happens to be 4. Another way to do this problem is you can actually take infinity and plug it in for x. So if I use direct substitution, this is going to equal, let's try this one in green. This one's going to equal 4 subtract 3 over infinity squared. Now I want you to think about a fraction that has infinity squared on the bottom. If you take 3 and you divide it by a really big number, eventually that's going to approach 0. And so this is why the limit is just 4. This fraction went out to 0. In example 3, we're going to find the limit of a rational function a different way. So one way you can do this is you can divide the numerator and the denominator by the highest powered term in the denominator. So the highest powered term in the denominator is x squared. So what we're going to do is we're going to take the limit as x approaches negative infinity, and we're going to take this original function, and I'm going to divide each term by x squared. So I'm taking each of those, 3 divided by x squared, 3x squared divided by x squared, and 1 divided by x squared. And then you're going to simplify. So here the x squareds will cancel, and here an x will cancel with one of those x's. And now what we're going to do is find the limit by direct substitution. So we're going to evaluate each part. Here, this is just 3. So on the bottom I have 3. 1 over x squared, if I were to plug negative infinity in for x and square it, the denominator is going to blow up into a really big number. And 1 divided by a really big number is going to be 0, or at least approach 0. Here, you can see I have negative 2 over a really small number, negative infinity, and that's also going to move to 0. And then 3 over negative infinity squared is going to move to 0. And if you're not understanding that, what's happening is if I put 3 over 100, and then I put 3 over 1,000, and then I put 3 over 10,000, you can see that this number is approaching 0. So when that denominator is really big and the numerator is small, that number is moving towards 0. This means that the limit is equal to 0. So the limit of this is 0. Now here's the graph. You can see as I move to negative infinity, you can see that this graph is moving towards 0. You can also see if you did it by horizontal asymptotes that this is bottom heavy, and bottom heavy has a horizontal asymptote of 0. So if we look at B, this equation, this rational function is approaching negative infinity. So when we're approaching infinity or negative infinity, and we have a rational function, we are going to be approaching the horizontal asymptote. So at negative infinity, where is this graph approaching? Or at positive infinity, where is that graph approaching? It's the same as the horizontal asymptote. So rational functions, when we're going to infinity, we can look at the horizontal asymptote. What is the horizontal asymptote of this function? Well, x squared and x squared make it same co, and so that limit is at negative 2/3. So as x is going left forever, f of x is going down to negative 2/3. Looking at C. At C, you can see that this is top heavy. And so if I were not looking at the graph and I wanted to use the horizontal asymptote, there is not a horizontal asymptote for top heavy. So the limit does not exist. So the limit does not exist. If you look at the graph, you can see that the graph on the left-hand side is going to infinity. Another way to write does not exist is you could write infinity. Technically, infinity is not a limit because you can't really approach it as you're moving towards infinity. Infinity is just backing up on you, if that makes any sense. All right, so we are done. I just wanted to show you, I worked out here doing the problems the other way, and that's by dividing everything by the term with the highest degree in the denominator. So this term is x squared. So you can see I divided everything by x squared. I simplified. That left me with negative 2 plus 0 and 3 plus 0, which was also negative 2/3. Again, if you have a fraction and the denominator is really large, that fraction goes to 0. On the bottom, I did the same thing. I took x squared. I divided every term by x squared. I simplified. This gave me negative 2 times negative infinity, which is positive infinity. You can see in this problem, in the numerator, I have infinity, and in the denominator, I have 4. 4 divided into infinity is going to be infinity, because 4 divided into a really large number is going to give me a really large output.